Record. All right, great morning, great morning. I'm here with Kaysen this morning, and I am Coach Helene, and this is our Empowerment Through Golf STEAM education series. So that's science, technology, engineering, arts, and math. And we come on every second Saturday of the month, and we discuss science topics as they relate to golf. And today we have something really exciting to share, and we're going to be talking about rocket science and figuring out how rocket science plays into golf. So definitely looking forward to sharing that information with you. Do you have any questions so far, Kaysen? Or like any intrigue, like what are we doing?
No, not yet.
Not as yet. Okay, so I will go ahead and get started with the video. So the first one is going to be just about rocket science. And when we watch it, I would like you to think about how the rocket itself is like the golf ball moving through space. Okay? And
Okay,
let me know if you can see my screen okay.
I can see it.
Okay,
Okay.
perfect. All right, I'm gonna start playing the video now. And if you want, definitely grab a notebook, pen, and so we could take some notes and discuss. Okay?
You heard someone describe a difficult concept as, it's not rocket science, meaning it's not as difficult to understand as rocket science is. Rocket science is synonymous with difficult subjects. Wouldn't it be nice to be able to say something like, well, I actually know rocket science, and I think this is more difficult than rocket science. After watching today's video, I think you may very well have the background to be able to say just that, because I'm going to show you how communication satellites work and how they are launched into orbit. Although there are several different types of satellites, these types are the ones that probably have the biggest impact on our daily lives. But to understand what these things do and how they're launched, you're going to have to learn something about, you got it, rocket science. And I'm hoping you'll find it's really not as hard as it's cracked up to be. That's coming up right now. If you've ever used a GPS app to find directions, or if you've looked up the weather for your town or watched a live TV broadcast from a foreign country, you have interacted with a satellite. Satellites affect our daily lives. There are almost 3,000 operational satellites owned by over 100 different countries orbiting the Earth right now, and thousands more are planned for the future. About 550 of these are in what's called geostationary orbits. Communication satellites are typically in such orbits. What this means is that the satellite appears stationary compared to the rotation of the Earth. It stays in the same point in the sky at all times. In other words, you can leave your satellite dish that receives your favorite TV shows in one position and never have to change it. So the question is, how do scientists calculate where to put the satellite so that it remains at the same point in space? Orbital mechanics is rooted in Kepler's laws of planetary motion, published way back in 1609. Newton's laws of universal gravitation, published in the Principia Mathematica around 1687, also plays a role in many calculations. Kepler's laws allow us to calculate the period and speed of such a satellite. Speed is the square root of mu over r, where mu is the standard gravitational parameter, equal to Newton's gravitational constant times the mass of the planet. R is the radius of the satellite from the center of the Earth, and the period has the following formula. Note that the speed and period only depends on the radius of the satellite, not on its mass. A geostationary orbit is circular, and since the altitude of the satellite does not change, its speed must be constant. If you do the calculations, you will find that the geostationary orbit is 35,786 kilometers from the equator. The orbital period is 23.93 hours, or 23 hours and 56 minutes. You might say, why isn't it exactly 24 hours? Well, 23 hours and 56 minutes is actually equal to one sidereal day. This is the time it actually takes for the Earth to complete one rotation with respect to a non-rotating frame of reference. The reason we normally count 24 hours as being one day is because 24 hours is the precise time that the sun is at the same spot in the sky every day. But you have to keep in mind that the Earth moves with respect to the sun. The Earth moves 1/365th of an arc around the sun during this time. That's about 4 minutes. In other words, the Earth has to rotate just a little bit more, about 4 minutes, before the sun is directly overhead. But one full rotation around its axis is actually 4 minutes less than that. Now the question is, how is a communication satellite inserted into an orbit? The first step in this process is to launch the satellite on a rocket that has the payload capacity to carry the satellite to this orbit and can impart the speed necessary to maintain this orbit. In the United States, one workhorse rocket for this task has been the Atlas V. This rocket weighs about 700,000 pounds or 317,000 kilograms at launch and can lift 28,000 pounds or 12,700 kilograms to geostationary orbit. 90% of its weight is fuel, which is typical for rockets. The main engine is powered by liquid oxygen and RP1, which is a highly refined form of kerosene, similar to jet fuel. How does a rocket work? First, a rocket does not rely on the atmosphere to oxidize the fuel like a jet engine does. That's because it carries its own oxidizer. This allows it to be able to function in outer space where there is no atmosphere available. A jet engine would not work here because there's no oxygen available to burn the fuel. Rocket engines are an application of Newton's third law. For every action, there is an equal and opposite reaction. The combustion of fuel causes high-pressure exhaust gases to be expelled at supersonic speeds. The rearward acceleration of this mass of the fuel leaving the rocket nozzle causes an equal and opposite reaction of forward thrust powering the rocket forward or upward during launch. The shape of the nozzle of the rocket is designed to increase the velocity of the exhaust gases further to increase its thrust. Highest thrust is achieved when the mass flow rate of the fuel and exit velocity of the propellant is high according to this equation. The fuel has to be delivered at high volume and pressure to get the thrust required for lift. This pressure is powered by fuel pumps that boost the pressure of the gases before entering the combustion chamber. Because these pumps can boost the pressure, the fuels do not have to be pressurized so high, and the thickness of their storage tanks can be reduced, resulting in weight savings and increased payload capacity. Now you might ask, how are these pumps driven? They're typically driven by using a small amount of fuel to drive a turbine which drives the pump. Now maintaining a stable straight flight is an issue. Early rockets were stabilized by large fins. For stable flight, the center of pressure where the net aerodynamic force acts must be lower than the center of gravity. This is because if its angle of attack changes relative to its flight path, the net force acting below the center of gravity can restore the stability that realigns the nose of the rocket. Modern rockets don't use fins though because of the extra weight and aerodynamic drag that they cause. Stability comes from swiveling the thrust nozzle to keep it stable. This is called gimbaled thrust. A geosynchronous orbit is achieved in stages. Typically the rocket will take the satellite to its orbital altitude, but the initial orbit is elliptical. This elliptical orbit has to be changed to a circular orbit to become geostationary. So for example, an elliptical orbit may take the satellite to an altitude of 150 kilometers at its lowest point called the perigee, and to the geostationary orbit of 35,786 kilometers at its highest altitude, the apogee. We can use Kepler's laws to calculate the speeds it will have at these points, about 36,500 kilometers per hour at the perigee and 5,800 kilometers per hour at the apogee. The laws of physics are such that the satellite continues on an elliptical orbit until something changes its orbit. This change is done by accelerating the rocket at precisely the right time during its trajectory so that it forms a more and more circular orbit with every pass around the Earth. The thrusters have to be turned on precisely at the apogee to accelerate the craft from 5,800 kilometers per hour to 11,000 kilometers per hour, which is the speed it needs to have to maintain a circular geostationary orbit. As you can probably surmise, there's only one geostationary orbit, and it is at 35,786 kilometers above the Earth's equator. There's no other geostationary orbit, and there are 500 satellites at that altitude. This real estate, even in space, is limited. The total perimeter available is about 265,000 kilometers. This wouldn't be a problem if each of the 500 satellites were placed equal distance apart. There would be 500 kilometers of space between them, but that's not the way the world works. There are many more satellites above the most developed regions of the Earth. They are sometimes less than 10 kilometers apart, and the speed at which they have to move is 11,000 kilometers per hour, or 3 kilometers per second. There's not much space. They're less than 4 seconds apart. The real estate here is a prized commodity, as you might imagine, and is tightly controlled by an organization called the International Telecommunications Union, or ITU, which assigns each satellite a slot at this perimeter. In addition, unless the rocket is launched from somewhere in the equator, it will have an orbit that is not quite geostationary because it will not be in line or in the same place relative to the equator. So for example, when satellites are launched from Cape Canaveral, Florida, which is located at about 28.5 degrees north latitude, the orbit will be inclined 28.5 degrees from the equator. This has to be adjusted, and this requires more fuel. It's beneficial, therefore, for countries to launch their rockets as close to the equator as possible so that less rocket fuel is needed to make this adjustment. In addition, launching from close to the equator gives the rocket added inertia because of the Earth's greater speed of spin near the equator, so that the launched rocket will already be moving at the speed of the Earth's spin at the equator before the launch. Note that not all communication satellites are placed in geostationary orbits. Some are placed in low Earth orbits too. Low Earth orbit satellites can serve the same function, but you have to use many of them as they're moving at such high speeds, and there has to be constant handoff of transmissions from one satellite to another. But the advantage is that these satellites are cheaper to launch and cheaper to make because they don't have to be as powerful, since transmission distances are a lot shorter. So what happens now that we finally have our satellite in orbit around the Earth? We have adjusted to make it a circular geostationary orbit. We have placed it in a correct slot assigned by the ITU, and we have adjusted its angle of orbit so that it is at the same plane as the equator. The first thing that happens is that the solar panels are deployed so that the satellite can have power to function. The main function of the satellite is to receive signals from the Earth, mainly in the form of radio transmissions, amplify them, and then relay them back at a different frequency back to the surface of the Earth. The shift in frequency is used to prevent interference of incoming signals with outgoing signals. Since radio waves are a form of electromagnetic radiation, same as visible light, they do not bend much around the curvature of Earth. Photons are too fast after all. The job of the satellite is to transmit radio waves over long distances. Otherwise, this would require a string of thousands of relay stations on Earth to do the same task. These satellites usually have at least 2 antennas, which may be aimed at 2 different points on the ground. Each is used for both incoming and outgoing transmissions. These antennas are generally made as large as possible for greater sensitivity in receiving signals from Earth, which can become quite faint by the time they reach the satellite. But the size is limited to about 10 feet in diameter or 3 meters due to the space restrictions inside the rocket. Interestingly, a geostationary orbit is sometimes called the Clarke orbit, named after science fiction writer Arthur C. Clarke, who wrote 2001: A Space Odyssey. Believe it or not, he was the first person to detail the usefulness of such an orbit in a story he wrote back in 1945. That tells you that science fiction can sometimes foretell future science fact. The next time you watch satellite TV or use your GPS app, listen to Sirius XM radio or check the weather, think about the rocket science and the incredible technology that goes into allowing us the privilege to enjoy these fantastical technologies. I'm excited to tell you about Squarespace, today's sponsor. Squarespace is a website builder designed to help creators, entrepreneurs, and anyone else looking to have an internet presence create a website regardless of their technical ability.
Okay. Let's see. Do we want to pause for any takeaways? I found a lot, but I also think it would be a good idea to jump into the aerodynamics video, and it doesn't necessarily highlight golf ball movement, but what it does I'll just stop sharing for a second. Okay, but what it does is talk about the movement of spherical objects through space, and that's what we're focusing on the golf ball, right? But there are a lot of parallels to the launching of a rocket and getting the rocket into perfect orbit that coincide with golf. I know there were a lot of equations there and a lot of principles and laws. I don't expect you to remember all of that. But you did say that you had a desire or interest in math. So if you keep on with that pursuit of math, like the laws and things like that, or theories, you're gonna start memorizing those and using them on like an everyday basis, especially if you went on to college on a like to study math, like if you wanted to become a mathematician, like that would be your new language, so to speak. So any thoughts that you wanted to share before we got into the other video?
From that first video, it said that every action has a reaction, and
Mhm.
that applies to golf because if you like hit the ball, it has a reaction where it will
Yes,
go.
yes, that's a great one. What is something else that was mentioned that's sort of similar to moment of impact on the golf ball? If you could think
What?
of if you could think of the diagram that they had with the globe in the center and the ellipse versus the circle, so an elliptical orbit versus a circular orbit around the planet. Do you remember anything there?
Oh,
Tell me.
like they have their it's like they have a certain speed they have to go to up.
Yes, yes, that is exactly it. So when we get to the moment of impact, because we always talk about nice and slow on the takeaway, but then you want to accelerate through your downswing and into the follow through so that you can actually get the ball up in the air so that they can actually like project. So that's exactly it. Oh my gosh, you're so smart. I love it. Okay. Anything else? Anything else that you wanted to share, or are you ready to jump into the next video? I think those 2 points were
Ready?
perfect already. Ready? Okay, I'm ready to. Let's do it. Let me share again. Oh, did I close the window? I'll just share. Okay, 1 second. Where did it go? Okay, here it is. So my tab's open.
Description. When fluid flows past an object, or an object moves through a stationary fluid, the fluid exerts a force on the object. We can split the force into two components, one acting in the same direction as the fluid flow, which is called drag, and one acting perpendicular to the flow direction, which is called lift. If the fluid is a gas, like air, we call these aerodynamic forces, and if it's water or any other liquid, we call them hydrodynamic forces. This video is going to focus on the drag force, and I'll cover lift in a separate video. Most of the time, drag forces are undesirable. They can have a huge effect on the fuel consumption and performance of vehicles, for example, and so engineers go to great lengths to minimize them. We'll explore some interesting ways of reducing drag later on in the video, including how the airline industry could save millions of dollars a year in fuel costs by using a drag-reducing innovation based on artificial shark skin. But to optimize the design of objects affected by drag forces, we first need to understand where these forces come from. So let's start by covering the basics. Drag forces are caused by two different types of stress, which act on the surface of an object. First, we have the wall shear stresses. These stresses act tangential to the object's surface and are caused by frictional forces that arise because of a fluid's viscosity. Then we have the pressure stresses. They act perpendicular to the object's surface and are caused by how pressure is distributed around the object. The drag force is the resultant of these two stresses in the direction of the flow. So if we know exactly how the stresses are distributed over the surface of our object, we can integrate them to obtain the resultant drag force. The component of drag caused by the shear stresses is called friction drag, and the component caused by the pressure stresses is called pressure drag, or form drag. Pressure drag is most significant for blunt bodies, like this sphere. It is essentially caused by a difference in pressure between the front and rear of an object. Pressure drag increases significantly if flow separation occurs, which is when the fluid boundary layer detaches from the body, creating a wake of recirculating flow. This creates an area of low pressure behind the body, called the separation region, and results in a large drag force. If you're trying to reduce drag forces, you'll want to minimize flow separation at all costs. Flow separation can also cause vortex shedding, which can generate unwanted vibrations and instability. To understand why flow separation occurs, let's look at flow on the upper surface of the sphere. As the fluid passes over the surface of the sphere, it is initially accelerating, and so pressure is decreasing in the direction of the flow. This is called a favorable pressure gradient. Beyond a certain point, the flow then begins to decelerate, and so pressure in the flow direction is increasing. This increase in pressure is called the adverse pressure gradient, and it has a significant effect on the flow close to the wall. If the pressure increase is large enough, the flow will reverse direction, and since it can't travel backwards because of the oncoming fluid, it detaches from the surface, resulting in flow separation. Flow separation occurs at around 80 degrees for a smooth sphere in laminar flow. If the boundary layer is turbulent instead of laminar, it's better able to remain attached to the surface, and flow separation is delayed until around 120 degrees, which reduces the pressure drag significantly. This is because turbulence introduces a lot of mixing between the different layers of flow, and this momentum transfer means the flow can sustain a larger adverse pressure gradient without separating. This is why golf balls have dimples instead of being perfectly smooth. The dimples generate turbulence, which delays flow separation, reduces drag, and allows the ball to travel further. This idea of using turbulence to delay flow separation and reduce pressure drag is also why some airplane wings have small vortex generators protruding from them. Bodies that travel through fluids, like plane wings or submarines, are usually designed to be streamlined in a teardrop shape to minimize the effect of flow separation. For
Sorry about the YouTube ads, my apologies.
For very streamlined bodies, like this airfoil at a shallow angle of attack, pressure drag is small because flow separation is significantly delayed or doesn't occur at all. For bodies like these, it's the wall shear stresses which contribute most to the total drag force. The drag component caused by these stresses is called friction drag. Friction drag increases with the viscosity of the fluid and is most significant for bodies which have a large surface area aligned with the direction of flow. We saw earlier that turbulence delays flow separation, which reduces the pressure drag. But for friction drag, it has the opposite effect. Laminar and turbulent boundary layers have very different velocity profiles. The velocity gradient at a wall is steeper in turbulent boundary layers than in laminar ones, and so turbulence produces larger shear stresses. So to reduce friction drag, you want to delay the transition to the turbulent regime and maintain laminar flow for the largest possible distance around the object. It has been estimated that obtaining laminar flow over the wings and fin of commercial aircraft could reduce the total drag force by around 10 to 15%, but this is very difficult to achieve. Techniques like hybrid laminar flow control have had some success. It involves using suction to pull air through small holes into the wing, which delays the onset of turbulence. Research has also focused on minimizing the friction drag associated with a turbulent boundary layer. When trying to minimize drag, engineers very often look to nature for inspiration. Sharks are a particular interest because of the unique microstructure of their skin. Shark scales contain microscopic ridges, which are aligned with the direction of flow. These ridges modify the turbulent boundary layer in the near wall area, and this has the effect of reducing friction drag. Research indicates that coating a commercial airliner with artificial shark skin of similar microstructure could reduce its total drag force by 2%, which would result in massive fuel savings for the industry. This approach has yet to be widely implemented on commercial aircraft, partly due to challenges associated with manufacturing, but this could change as the technology improves. We've seen that the magnitude of pressure and friction drag depends on the geometry of a body relative to the direction of flow. The most obvious example of this is a flat plate. If we position the plate at 90 degrees to the flow, it is a blunt body. Flow separates easily, creating a separation region, and so the pressure drag is large. But the friction drag is almost zero, since shear stresses aren't aligned with the drag direction. If we rotate the plate by 90 degrees, we now have a very streamlined body. The pressure drag is small since there's no separation region behind the body, but the friction drag is now much more significant. This logic also applies to airfoils, where the angle of attack has a large influence on the drag force. At high angles of attack, separation occurs, which significantly increases the drag force. When streamlining a body to reduce drag, it's important to remember that friction drag will increase as the pressure drag reduces, and so these two aspects need to be carefully balanced. The shape that has the smallest total drag force won't necessarily be the one that is most streamlined. I mentioned earlier that we can integrate the pressure stresses and the wall shear stresses to obtain the total drag force. The problem is that in the vast majority of cases, it's pretty much impossible to know the detailed distribution of these stresses, and so we usually represent the total drag force using the drag equation instead. The CD term is the drag coefficient. It captures all of the hard-to-measure parameters, like the effect of the geometry of the object or the effect of the flow regime, and can be determined either experimentally, using a wind tunnel for example, or by running numerical simulations. The other terms in the equation are the fluid density ρ, the free stream velocity v, which is usually assumed to be steady and uniform, and A, which is a reference area that will depend on how the drag coefficient was determined. For airfoils and other streamlined bodies, A is usually the planform area, and for blunt bodies, it's usually the projected frontal area. The drag coefficient can vary quite substantially with Reynolds number. Let's look at how it varies for a few different two-dimensional shapes. For a flat plate oriented at 90 degrees to the flow, the drag coefficient doesn't vary significantly with Reynolds number, because flow separation will always occur at the edge of the plate, and so, although it is a blunt body, it isn't affected by whether flow is laminar or turbulent. For blunt shapes like this disc, we see a large decrease in the drag coefficient at the transition between laminar and turbulent flow, because flow separation is delayed when the boundary becomes turbulent, reducing the drag force. And for streamlined bodies, the drag coefficient reduces gradually as Reynolds number increases, since viscous forces are less significant at higher Reynolds numbers. But the drag coefficient begins to increase after the transition to turbulent flow, because, as we saw earlier, a turbulent boundary layer produces larger shear stresses. For a sphere, the drag coefficient graph looks like this. One interesting thing about this graph is that it's a straight line for Reynolds number less than 1, and the line is defined as 24 divided by Reynolds number. At these very low Reynolds numbers, flow separation doesn't occur, even for very blunt bodies like the sphere, and so all of the drag comes from friction drag. Plugging this equation for CD into the drag force equation gives us an interesting expression. This is called Stokes' law, and it is an exact solution for the drag force acting on a sphere for Reynolds numbers less than 1. It's one of few cases where we have an analytical solution for calculating the drag force, and it has some very useful applications. We can use it to easily calculate the terminal velocity of a sphere falling in a fluid, so long as Reynolds number is low enough. As a sphere falls through a fluid, its velocity will increase, and so will its drag force. Terminal velocity is reached when the weight of the sphere perfectly balances the drag force, so that the sphere stops accelerating. The drag force is defined by Stokes' law, and the weight of the sphere is easy to calculate based on its volume and density. We just need to remember to subtract the density of the fluid as well, to account for the buoyancy force. And so, based on Stokes' law, we can obtain this equation for the terminal velocity of the sphere. We can apply this equation to create a viscometer, which is used to measure the viscosity of a fluid. To do this, a sphere is dropped into a tube of liquid, which is long enough that the sphere will reach terminal velocity. The terminal velocity can be measured by timing how long it takes the sphere to pass between 2 points marked on the tube. And so the viscosity of the fluid can be calculated using the equation we just derived. We know that pressure stresses and shear stresses are the two fundamental causes of drag. But in some cases, specific components of the drag force are named because of how they're caused, even though they're just different forms of pressure or friction drag. In aviation, for example, 3 important sources of drag are induced drag, wave drag, and interference drag. If you'd like to learn more about these sources of drag, I've covered them in the extended version of this video, which is available now over on Nebula. For those who don't know, Nebula is a video streaming service built entirely by educational creators. It's home to some of the best independent creators out there, including Mustard, Real Engineering, and Practical Engineering. It's a place where creators can experiment with new formats and longer videos. So, in addition to their normal content, which is completely ad-free on Nebula, you can explore exclusive Nebula originals that you won't be able to watch anywhere else, or dive a little deeper with bonus content, like the extended version of this video, where I've replaced this ad with a look at induced drag, wave drag, and interference drag.
All right, I'll just stop the video. I think we are getting low on time anyhow. Okay, well, it's not even showing me the timer. So let's do a recap really quickly. Oh, I wonder what happened. Sorry about that. I didn't intend to stop the recording a while ago if it did.
It's fine.
Okay. So recap on that one. That was also very detailed, a lot of equations, but really great explanation though. That's why I wanted to share it. So what were some of your takeaways, or what did you like best about what you saw?
Both those have those like little holes in them, like ridges, because to minimize or like lessen the drag force.
Correct. Yeah. So that's why golf balls have dimples. So they were talking about the shark skin and how, scientists want to emulate that for airplanes. But so instead of having that on a golf ball, we have dimples. So yes, 100% correct. And it also affects the spin. So when they were talking about the, I forget the actual term that he used, excuse me, but in the separation region behind the ball, and there were some vortexes forming. So essentially, when you think of a golf ball moving through the air, that separation region behind the ball is also what generates or creates the spin of the ball. So it's either going to keep it straight down the line, move it to the left, or move it to the right. Okay. Awesome. Any other takeaways? I know it's probably going to end like right now.
No, nice. No.
Okay,
Sorry.
well, I thought this was a great session. You can give any last words, comment, feedback, and then we'll just wrap it up for today. But rockets and golf ball launches. Anything from you?
What?
No? Okay. All right, well, this was our STEAM education call for the month of March, and we discussed the relationship between rocket launching and launching golf balls down the middle of the fairway. So until next time, see you then. Thank you.